So thanks for joining us all today at this webinar about LoRaWAN. We're going to talk about LoRaWAN today, and especially about industrial sites for LoRaWAN. So I think we all know in LoRaWAN as a generic wireless protocol is quite broad in use case and everything else. But focusing from our TWTG, we're focusing on this industrial type of IoT solutions. So it only makes sense that we talk about the industrial sites with this LoRaWAN applications. I'm not here today alone. I have Clement with me, our radio frequency expert. And later on, we will be joined by Martijn to talk more about the network server side, which is more on software implementation. But all that in set time. Before, you might know us from our Neon product line, which is LoRaWAN based. There it is. Small devices that can be used all around an industrial site to do condition-based asset monitoring. Basically to check small assets or inputs to check if they are on or off, hot or cold, open or closed, like the smaller ones of type of devices. And when we started developing this hardware, we actually made the decision to do it on LoRaWAN, which is a decision that actually doesn't come too naturally. LoRaWAN is not a technology that's been around for that long, and it has been quite hefty, basically, in development when we started this. I mean, making a product ATEX approved and certified completely that it could be used in your type of situations. It took us about 2 years to make the first product there. And with this 2 years, LoRaWAN actually protocol came a long way as well. So we're really happy with that. In the end, I think we still really feel confident we made the right decision, but we see that LoRaWAN gets more and more traction in the industrial sites as well. So what makes an industrial site so different than other sites? In order to, we think it deserves a complete webinar just to talk about LoRaWAN in this space. Actually, one of the first things is, I think, the amount of certainty you want to have from a network. So this is a mission-critical operation with a lot of dependencies on each other, and it's not something normally a place where you would just innovate and just try out stuff. This is heavy industry. If something goes wrong, it has a lot of impact, obviously. There's a lot of machinery in there, heavy, more expensive equipment. So it's not a technology where you would, or an environment where you would expect new technology just to pop up and just to pilot. Nevertheless, if there are efficiency gains or new ways that actually the technology can make a really big impact, you might see that it has its way to this industry as well. But then when it's there, it's not there just for a year or 2 years. You want something that's reliable over this longer period of time. It needs to be secure. It needs to be dependable. That's all topics we want to discuss today. That's why it, in our opinion, makes the technology ready for industry and not for any other industry. And I think that's also why we made this LoRaWAN decision back then when we started it. It's not that LoRaWAN is the only wireless network. I think when you look at wireless networks, there are a lot of options. Some of them only used in consumer spaces, where you look at Bluetooth or other types, others using in business to business, but more of industry business, but not really the industry business, but more business to business in logistic trackers, or asset trackers in buildings, or smart buildings and smart cities. And all these use cases actually has their type of wireless connection. When we normally talk about wireless connection, I always take the example of a mobile phone, which is not like a one single device as well. It has different type of technologies in there. It has Bluetooth to pair with your car kit, Wi-Fi at home to stream, and a cellular connection when you're outside, and to call or do voice, and even now data sets. And the same goes for this type of industrial wireless networks. There's not one to rule them all. It's not that one is better than the other one. We have a lot of different options, and all these different options has their own use cases. If we look at LoRaWAN, I think in the industry we see it most compared now with private LTM or 5G type of rollouts or existing wireless cards, which is, from a wireless perspective, I think the most common ones that either being rolled out now or have been rolled out the last couple of years. And if you look at LoRaWAN, you can see that it has a quite different type of footprint based on the, if you compare those technologies together. Where LoRaWAN really excels is battery life. So it really can stay out of the field for years without even being too hard in engineering. So even when you engineer it, if you do normal, you don't have to really take a lot of measurements, really expensive batteries or really huge battery packs or energy harvesting technology in order to achieve 5 or 6 years of battery life reliable. It has huge range. So that means that from the gateway network, which we're going to discuss a lot today, to the end node, you can have kilometers of range even in open fields. That's something that will make the installation costs and the infrastructure quite cheap. But all this upside also comes with a downside. So if you look at bandwidth, there's other technologies that have higher bandwidth, so they can push through a lot of data. And transmission latency. LoRa does have quite some long latency if the sensor one comes to the other. When I talk about a lot of latency, it's still seconds, but still it can be for some use cases really big difference versus milliseconds in other industries or other installations. But yeah, those latencies come with a price at power consumption when you see LoRa really excel. That is the trade-off where we see if you make your decision on what kind of sensor to use, there probably will be use cases where wireless HART makes a lot of sense, and you probably just need to go for that. There are use cases where it just makes a lot of sense to go to a private LTE network and roll that out on your site. A lot of these sites also use Wi-Fi. I mean, it's not even in this comparison, because from our point of view, Wi-Fi is really more for device, and a lot of higher bandwidth, really high bandwidth interfaces with tablets and mobile phones, and really doesn't handle thousands of devices on the site at all. I mean, for people at home, 50 devices on one wireless router is already way too much, let alone handling 10,000 of devices at a certain site. So that all made us decided to do LoRaWAN as an industry standard. Industry standard. That's when we started it three years ago, basically, when LoRaWAN just started, and it actually evolved from there. Because a small history lesson, LoRa does not existed out of nowhere. It actually started in a small lab. IBM had a big part of it. And with that actually became to Semtech, which is a chip manufacturer, a radio chip manufacturer that makes small black silicon boxes that need to be integrated in devices. And if people say LoRa is free or whatever, it's not open source, it's not free. But the beauty of LoRa is you only have to pay the license once when you buy that small radio chip. It's a couple of cents, and basically we already paid it for when we put it in our devices. So with that one-time fee, you actually have a free subscription for the rest of the time to use that LoRa technology and modulation. And everything else that comes around LoRa that needs to be worked with LoRa is open source. So you can find software stacks and everything else. And there is a really big community working around LoRa, developing those kind of things. We see LoRa networks as the Things network, which is like a global scale LoRa network, operating in this open space. Which is great. It really enabled LoRa, really kicked off the development, and we saw a lot of interest in there, which made a lot of chip manufacturers there. We have gateway manufacturers, so the whole ecosystem actually builds on top of that. That's where you also see a comparison, like the other comparison we did on a technical level, but on an ecosystem level, LoRa really enables a lot of developers to start working with it, which happens. So you see a lot of device makers coming up now. We see other industry leaders coming with LoRa devices. We see companies like Cisco building gateways. And all this more and more also into an industry protocol. And we're talking about industry today, but LoRa actually found its way already in smart city hubs and smart buildings. Well, granted, a less demanding environment, but it was a great proof ground basically for LoRa to see how it performs well under stress with thousands of devices. And like a smart building concept is from an RF point of view, not an ideally place as well. And, monitoring, workplace monitoring, and those kind of things. There are still a lot of sensors that has not the same kind of dependency, but really scaled up the protocol so that it worked. The beauty of LoRa, which is the final point, is why we think it really deserves a second look for our industry platform, is that it can be public or private. Public is easy, it gets you started. That's where you look at the Things network. You're depending basically on anybody that will just put his gateway in his own power socket and to his own Ethernet connection, and basically shares the network with you, which is great. You have network probably 80% of the world from big cities already have coverage from the Things network, fully aware now. On industrial sites, it's not that much, but still. If you're at home, if you have a smart garden, you put your moist sensor in your garden, there's a really big chance you have a LoRa network in your range. And if it's not the Things network that's free to use, there is probably a network operator near you that will cover your country with a network just like it would do with 3G or 4G. And then they also host that whole message chain for you. And that's the downside, obviously, for public. You are quite dependable on a third party. But where a wireless network like 3G or 4G can only be done publicly, this you can also do private, just like you do your Wi-Fi network. So if you look for LoRa, it's really comparable with a Wi-Fi network that runs privately complete with your own IT department, fully managed, fully secure, end-to-end, but all the way expanded to a public Wi-Fi at your local Starbucks, where you probably would not want to plug your laptop in, but the protocol is the same. The laptop and the gateways are the same, so the protocol speaks in the same way, it's just differently managed. And it all goes without licensing or radio operations or expensive frequencies. So to take LoRa private for an industrial site makes a lot of sense. You build your own network, all data stays within your own control. And basically you have your own network without having to do a complete license operator, without really having expensive equipment, and still leaning on all that knowledge that has been made in the public domain, but then leveraged to your private website. So when I talk about LoRa equipment, it's basically a whole tool chain. That's something that I want to focus on today. The end nodes, we make that every day. So if you want to talk about nodes, I think today we're not going to talk about our devices anymore. For all we say, it's either our device or anybody else's LoRaWAN device. That's the beauty of this whole platform. If it's LoRaWAN compliant, it will work. You need a gateway. So that's basically your antenna, your router, something that transmits to radio. The next phase is you need some software, network server. An application server, and in the end, this is all need to have, but what you want to have is a dashboard, something that you plug your data into, have actions or follow up with that. So that's the general introduction, and of course I need more input for the next steps. I think it might be good to remind you that while I'm just talking, and I'm not going to talk with Clement, and I'm going to talk with Martijn later on, that you probably have a lot of questions yourself already. So there is a nice chat function in this webinar. Please shift your questions there, and we'll try to cover them at the end of the webinar to follow up with those type of questions and see if we can fill you up and make you all a little bit more smarter about this whole LoRaWAN protocol. The first stuff that we're going to do is with Clement, and it's focusing really in depth on the LoRa modulation. And that's something, before I hand it over to you, is with LoRaWAN, it's always been spoken as LoRaWAN in total. But actually it's compiled about two different type of things. LoRa by itself is just a modulation technology. That's something that goes through the airwaves. It's something just how a device with the gateway talks to each other. That's really about a wireless protocol by itself. And the WAN is basically the network protocol that handles 10,000s of messages over the same network coming in through different type of gateways, end-to-end security in the whole message protocol, message structures and everything else. That's the second half of this talk, so that's what we do with Martijn. But the first half about radio frequency we're going to do with Clement. So you're sitting here already while I'm talking. Clement, when you turn in your slides for this presentation, you put this elevator picture in there. Why?
Okay, so hello everybody. I put an elevator here because I think it's represents a good feeling of lack of network that normal, let's say, everyday life people can have. So when you jump on an elevator, most of the time you don't have a network connection anymore. So you can guess that it's kind of a harsh environment already. But what about this one then? So that's the thing.
Basically comparing the industrial sites to elevators.
Yeah, and it's actually even worse because radio waves doesn't like big walls, doesn't like metal environments, and that's basically what industrial site is. It's only metals and big walls and big distances. So that's the thing. So today I'm gonna bring you a bit over the trade-offs.
This looks technical, man.
It's okay. It's gonna be okay. I'm gonna bring you a bit over the trade-off of choosing a correct protocol, wireless protocol, and I'm gonna try to bring you from the device to the gateway, like we were the RF signals together. So the first stuff I want to mention, and it's kind of where the webinar, at least my part, will rely on. It's a link budget. So a link budget, it's a number that you use to define how many obstacles or how many losses you're allowed to have between your transmitter, so in our case our sensor, and between your receiver, in our case a gateway. So in between this, the signal has to go through, and in between you're allowed to have a certain number of losses if you want to be sure that your signal arrives, that you can hear the signal at the end. So this number is called the link budget. So you can see over here you have a few different link budgets. So this is only LP1's networks comparison. For example, Wi-Fi has way lower link budgets, around 100, and this one are around 160, 150, 160. LoRaWAN depends on the spreading factor, we'll see that later, but let's say it's around 150
So basically, it's comparable with the volume that my neighbor's stereo goes to.
Exactly.
So LoRaWAN, the volume of my stereo just goes higher.
That's exactly that. If you have a baby screaming in the next room, you will hear less your music than if you don't have this baby screaming. And this baby screaming is basically the environment, the harsh environment.
But in this case, the higher volume is better for us.
In this case, it's better for you.
Okay.
But you have other ways to mitigate that. So that's what we're going to see later on. So with all these figures, LoRaWAN had a pretty good score. So why so? So we're going to see that in the next slide. So one of the main features why LoRaWAN has this big link budget number, it's due to the sensitivity of the device. So sensitivity is how low of a sound or wave are you able to hear. So if you have a better hear, you're able to listen me even if I'm go further, even if I talk at the same tone.
Makes sense.
So that's the beauty of LoRa. It's the sensitivity of the gateway and of the device is really low. And to achieve that,
really high, basically.
Yeah,
it's a high sensitivity.
It's a high sensitivity. Yeah. And basically, to achieve that, there is multiple stuff. And the first secret is laying on the modulation itself. So the modulation is the way that you transfer electromagnetic waves over the air, and the way of you encode information. And to encode information in LoRa, they use chirp. So it's frequency chirp. So basically, what you do is you have a single frequency, and then you increase a bit this frequency up or down, and depending if you increase it up or increase it down, then it's a 0 or 1. So you encode differently the information. So here you can see on the figure 2, it's an up chirp modulated signal. So it means that the frequency is going up. So you see the waves that is contracting on each other because the frequency is going higher. And you can see on the figure 3A that it's an up chirp. So it's go to the up the frequencies. So that's the first step. So you up and down, and by doing that, you're really interference proof because the other signal cannot really reproduce that kind of shape. So it's really interference proof.
So it's basically a trick to make sure that even if there is some other frequencies, other wireless signals, you actually move up because you're sweeping. You're going to all frequencies.
You're going to all frequencies, so you're more agile and you're able to. If someone else is transmitting on a single frequency, then you will know that it's not you because you will shift away and back and forth.
So it's easier to follow for.
So it's easier to follow for the receiver. Yeah. And there is also a great advantage of using this modulation is that with this frequency you can play over the time that you're sweeping up or down. And this what's going to be the spreading factors. And as you can see on the second pictures, it's like the different 1, 2, 3, 4, 5, the different widths.
The different angle, basically.
The different angles are basically a longer or smaller sweep. Mm-hmm. And if you have a longer sweep, then it's easier for your receiver to decode the message because he has more time to know and to make the difference of what's the number you're sending to me. So if it's longer, then it's easier to detect.
Because the height is also time, right?
It's also time. Yeah. It's time over frequencies.
Yeah. So, but the message takes longer to transmit.
The message takes longer to transmit, but then it's easier to decode, so your sensitivity is higher, so you can listen better because it's easier for you to decode. So that's basically how it is. It's mainly the modulation that it's really small boundaries and really particular techniques that have been developed by Semtech.
This is really unique, right? This is what LoRa. There's no other frequency.
This is not an unknown modulation technique, but it's really innovative to put this in the field of consumer industrial wireless telecommunication and with such a small bandwidth. Well.
If you talk about LoRa, you basically talk about this.
That's basically what it is. Yeah. It's the beauty of for people like me. It's the beauty of the.
Everything else you just need to have. This is the core. This is what
the core of it. It's basically the core of it.
So ask questions about this if you don't understand it, because this is hard.
So basically, what the length and the time that you spend to do your up or down chirp, frequency chirps, that will do in LoRa. It has been standardized, and then came out the spreading factor. So if you see, for some of you that are a bit familiar with LoRa, you have spreading factor for 7 to 12, which are different lengths of timing of sending the message.
So spreading factor 12 was basically the image that we saw just now. That's the
bottom one.
That's the bottom one. That's a long message.
Long messages. So you have more time, but it's on the air for a while. And if it's on the air for a while, it means that you have to send for a while. So if you have to send for a while,
a lot of power.
It takes you a lot of power.
Battery
power. And also, if it's on the air for a while, if you have multiple devices that are in the field and are sending twice or 4 times longer in the air. More device you have, more interference, and the more your air is crowded by a radio signal.
So that you really you have 2 reasons basically to try to use as lowest spread factor as possible.
So and that's what our devices are doing, and most of the LoRa industry is now going through that. It's adaptive data rates, so you start with spreading factor 7, and you see if you can reach your gateway, and if you can reach your gateway, you're okay, and if you cannot reach, you try to 8, 9, 10, and then it gives you the best.
So it's like an automatic calibration.
Yeah, that's basically the cruise control of.
It will just start shouting really small and short, and as soon as the message received, then it knows, oh, this is the maximum.
Exactly. So this is here on the left. You can see that of course you have more range, and that's what I was speaking just on the previous slide. You have more range if you go on spreading factor 12. They talk about tens of kilometers. 14 kilometers for the story is actually the Hertz curvature limit. So if you are on the sea level, you cannot go more than 14 kilometers because the Hertz curvature of the Earth will.
If the Earth is still round, then this will work.
If it is, for those who believe in that. Otherwise, yeah. And then if you go over on spreading factor 7, the sensitivity then is a bit lower. So then you have less range, of course. But depending on your application, it doesn't matter. Range is not always a key of workshops. So it's all,
because this range is just something in an open field, right? Because
of course,
like we said, we are almost in an elevator in this case, so this doesn't really apply to.
And that's what we're going to see next. Is all the ranges and stuff are given by open field. So
yes,
yeah, thanks. So this is basically the bus between TX, which is our device, and RX, which is our gateway.
So the transmitting power and receiving power.
Transmitting and receiving entities. Yeah. So if you see at the bottom, you have a dot line, which is a receiver sensitivity. So it's the level, the gateways of power, signal
That's the
power.
sensitivity of. If you are below that, then we lost the signal.
Then you cannot hear it.
It won't work.
It's lost in the noise, and the gateway cannot hear you or cannot hear you. So we're gonna slowly go from the device to the receiver. So if you see one of the main factors is actually in the one in the middle, what we call the free space loss fading. So it's basically the losses over the air. So when a signal travels through the air, every time you make some steps, you lose some energy because you spend this energy all around you. So then this energy loss. So that's the main factor of losses. And that's when the manufacturer give you range estimation. That's on what they base for.
Okay.
They just base on the empty free space.
But in the first 3 parts, what's that? That's the
The first part is the power that you're sending. So here it's an example of 14 dBm. So that's the power that you're sending on the device.
That goes outside the radio.
What is goes outside
on the device.
It's like the energy you get available, and you need to go somewhere.
And then it goes to the connector, and then to the antenna that actually helps a little bit.
Connector that you can be a degrader signal. Yeah. Antenna that can help you, and can play against you.
That's very good design or bad design.
So depending on the design, helps you some decisions as well that you want to make. But we'll talk a bit about it a bit later.
And then it actually leaves the device. It goes into open air.
Is the device do its journey over the air? So you can see the dump.
And then the receiver. Still, again, a good antenna can help a little bit again.
Again, you can.
But that's only small margins.
Small. The main factor, the main playing factor are in the middle. But indeed, you have some tweaking on the side as well for fine tunings.
Okay.
So this is an example here of a Vopak site. It's a Vopak here in the Netherlands site. It's a big site. It's like 2 kilometers, 2-3 kilometers.
And this is a particular terrible industrial site, as you can see that it's really packed together. So this is for vegetable oils and everything else. So you see that the tank terminals actually are close by. This is like the worst case that we had. All radio planning and site visit that we did to make a good radio plan for LoRa. I think this was by far the worst.
Yeah, that's the worst case. Yeah. But that's a good example.
That's good that you used it for this. So, okay, normally if we would help like a client to do this from LoRa, they will say, okay, I want a full coverage network.
If it's a 2D map without any with a flat terrain, then you can put one gateway here and it will go easily.
Yeah. If it would be an open football field, one gateway in the middle, no problem at all.
You will cover the 2 kilometers easy.
But one gateway here probably
one gateway here will not do the job, because in the middle you can have tanks. You can have boats, you can have trucks, whatever. So that's
Your free space loss is just too
free
much.
space. It's an hypothesis that you do, but this is validated. Yeah. It doesn't work. You're not in free space. So what you can do on another end is look at what kind of losses you will get. So you look at how packed you are. So you can cut the site into multiple zones and then try to estimate how much losses you will get.
Per zone, we're looking at obstructions, buildings, density, type of materials as well, right?
Type of materials as well, but mainly density. And as it's almost an industrial site.
But this means that you are on that site with your full gear helmet on and you actually take measurements.
That's part of it, actually. Yeah. That's part of it. You can do it theoretical, but sometimes it's good to see what's actually out there.
Oh yeah.
So once your signal left the device and go to this harsh environment, you need to reach a gateway. So multiple gateway providers are available. Most of them are now, as John mentioned in the introduction, focused also on industrial applications. So with root gateway, with multiple connectors, diversity antennas, multiple connections,
backup
powers.
For argument's sake, this is a shoebox with a couple of antennas, right?
Basically.
Okay.
So those gateways, I'm not going to compare them today for two reasons. The first one is because they're almost all the same. They all make with the same standards. And as we mentioned just before, the gateway part that is played on the radio level, it's only those small stuff at the end and at the beginning.
It's important, but not that important.
So it makes sense, but it's not that important. And when you have high standard manufacturers like TWTG or Cisco, they're gonna ensure that you have a good part here. But so there are similar characteristics. Maybe Martin could say later on about maybe some of different softwares, stack embedded, or some software possibilities, or output, output, but most of them are the same. But one thing that you should know when you do plannings and when you plan about running a network about your gateway is more where you're gonna put it and how you're gonna put it than which one you're gonna take.
Makes sense.
Basically. So here's, we have two slides. The two upcoming slides are about the installation of the gateway. First thing is the gateway needs to be installed pretty high.
The higher the better, right?
Because higher the better, because radio signal travels straight. They don't, a bit on the side as well, but most of them they travel straight. So if you want to reach every point, you need to be almost able to see every point, yeah. or see them, or being able to have enough power to go through the stuff that you don't see. But when you have a big tank in the middle, it's difficult to go through, so you better see. So the first step is put it high. Avoid obstacles, put it high. You also have a second advantage if you put it high. It's for damage or stuff like that. It's also easier to avoid.
Yeah, so nobody's driving.
People driving,
standing in front of it. Like if a truck parks in front of a gateway, the higher it parks, you don't have obstructions.
That's a good point. You actually give you a
stable.
You can ensure that your connectivity will remain the same.
But this looks like a normal good installation, right? You have your gateway down, so that means that it's easy to maintain on top of below your radio tower, and then you go with a couple of cables up to your antennas.
That's not a bad installation, but that's a good installation for your garage or something. Yeah. because the problem here is it's easy to access a gateway, but it's also easy to damage it. It's also easy for someone to, I don't know, turn it off, or the power, if the power is running, etc., etc. But you also have one other big problem that I see here with my radio expertise, is that the cable that goes from the gateway to the antenna is really long. And as we mentioned at the beginning, this is also one factor of losses in the signal. So if you have a long cable running, the radio is really sensitive, so it will fade over this thing. And here is a way better installation. Because here the Ethernet cable doesn't matter, it's just data flowing through. And then from the gateway to the antenna, you're really close, short distance, so you don't lose any power, you don't lose any energy.
This is just one of the examples to get that maximum range.
That's one of the tricks to get the maximum range. Of course, there is thousand more, but we don't.
Not giving it all away today.
So this is not the official planning that we made. It's one of the first worst case scenario evaluation that we made.
It was the worst case, right? Yeah. Without validation on site.
Without validation on site, we validated this on site, and we did some tuning and removed one of these gateways. But basically, what you can see here.
So the first design was with 7 gateways.
Yeah, I think 6 or
Yeah,
7.
Yeah, and you finalized with 5, right?
5, and then we got 5. We got 5 because of field testing, and that was not as pessimistic as me. so
You're always too pessimistic. Yeah.
Always. So here you can see, for example, the red circles on the bottom left, for example, is in the zone where it's way more crowded. So the certainty of receiving the message.
And this is designed for really low spreading factors, right?
This is designed to keep under spreading factor 9, and to also, it's also a good thing, we on industrial side, you don't want a gateway to let you down. So you don't want to rely on one gateway. So you also need to have at least, our rule is to have at least 3, but then you can accept 2 gateways that are picking up your messages.
So that means that if one gateway falls out,
your data is still transmitted.
There's always full redundancy.
And that's the beauty of LoRa as well. It's not a pure network. If one gateway sees your device, then your data will be there. There will be no problem. So we always want to have minimum 2, most of the time 3.
So 300% coverage.
To be sure, if one device, one gateway fails, you're still running. If one gateway is damaged, you're still running as well. And if a truck or something parked in front of your gateway, if someone got maintenance, put some stuff, you're still covered.
You're covered.
And this is kind of the data you don't want to play with, so this makes sense to have triple redundancy.
Good.
On this thing.
Okay, I think that was your part for now.
Yeah.
Thanks for that. We'll see if you get questions later on.
I hope they will.
We'll see. Try to challenge you. I think for the net part, this is where we talked about the LoRa part. So this is really about LoRa modulation, about your radio protocol. But LoRaWAN by itself actually has a lot of network.
Hi, everybody.
So the network server and upstream, basically, that's where the data gets handled. So everything downstream is basically the dirty work. We need to get into poles, we need to check on site, we need to build that radio. But as soon as the network actually is inside the gateway, it goes to what we just saw, an Ethernet cable, to the next phase in the system. And that's where you come in, right?
Yeah, that's true.
Yeah. So, you want to start with this one?
Yeah. So the next one is fine as well. This one is good. Yeah. So the gateways usually connect to a network server, and the network server handles all the low-level networking stuff. So all the lower-level protocols. Also, they connect multiple gateways to one server. So
because if you have triple redundancy, that means that every message gets at least 3 times in the network.
Yes, if you have, for example, 5 gateways, and a message is picked up by 3 gateways, it will end up in the network server. And so the network server takes care of the low-level networking stuff, but also deduplication of the message before sending it on to the application.
So it cleans basically the data.
Yeah, so after the network server you have still encrypted but deduplicated messages.
Yeah, makes sense.
Yeah.
But that's really specific for LoRa as well, right?
It is, yes, yeah.
So like a normal Wi-Fi network doesn't need a network server.
No, that doesn't. Yeah. Well, usually there is in the Wi-Fi network there is the same protocol, but it is on the different mediums, so a radio or a cable. And so the Wi-Fi access point is just routing those packages from one network to another. And the network server is basically really handling the network from deduplicate all the messages, because we have multiple access points on a single site.
Messages can take different time to arrive based on the spreading factor.
Yeah, and we also need to take into account, for example, if you want to send a message back to the device, which gateway has the best signal to that particular device. So which one should we take on? Yeah, because the devices cannot handle signals from multiple gateways. So,
Okay, and then what an application server? Because
application server is a part that you would use for really managing your fleet of devices. You can also do the final decryption of your message payload. So there's 2 levels of decryption that we come back to later. And the application server can also perform processing stuff like the messages come in as a binary blob, and you can make a nice JSON of it for further connecting to your network or to your systems down the stream.
And the join server, because I know internally we talk a lot about this.
Yeah, so the joining is a process of distributing keys between basically handshaking and key negotiation. What you can do is
because back in the early days when LoRa just started, we just pre-programmed the keys in the device as a fixed.
Yeah, it's the easiest thing to do.
Yeah.
You just say here's your key, and that will just work forever.
Yeah.
But because the keys are only 128 bits,
it's not that secure. Yeah.
you can somehow, if you listen long enough, you can calculate back the keys. So we want to.
And that means that our clients always have to trust us because we program the devices with keys.
Yeah, that's an extra complexity that you need to make sure that the keys are really secured at the source also.
So let's not use that anymore.
No, so what we do is we provide our devices with it's called an application key, and that key is put on the device, but it is a single key that is only used for negotiating a new pair of keys actually, and those two keys are then used for further communication, and that process is called the join process. Yeah,
we're gonna go into that later, right? About that.
Yes, we can talk about it later. Yeah.
Should we next slide?
Next, good, yeah. So here you see a whole layered diagram of the LoRa protocol. So there is the physical level, and all the OSI levels are here, and the MAC. And
so this is basically like LoRa is like it's not an open telecom line. It's like sending a letter, right?
Yeah. So
you're
a
message in a bottle, basically.
Yeah. So you're not getting nicely pre-configured JSON blobs or files, but you really have to do the whole network stack.
So this is basically the envelope in the envelope in the envelope to
exactly
deep dive, basically to in the end find if that file was open or closed.
Exactly, yeah, and all that is taken care of in the LoRa server, in the network server, I mean, and in the application server, yeah. So if we can on the next slide, we zoom in on the second layer, and here you can see this is the part where it gets interesting because the MAC payload is actually also contains the frames and the real data for the application.
That's why you went through all this trouble, basically.
That is the sensor data, yeah. And so there's some code on the end to verify that your message was sent correctly, and there's a header that contains information about this is, for example, the type of message that you want to receive. This is a join message, or this is a real payload message, or stuff like that. And then the payload itself. So the package is encrypted with the network session key. So that gives you encryption from the device until the network server. And then from the network server, the network server can then pass on the payload to the application server.
Basically, a second layer of encryption.
Yeah, so that means that if you are on, for example, a public network, your payload will travel through the network server of the public network. It's not your own. And so the package will end up in your application server or in your application, wherever, still encrypted. So you have end-to-end encryption there. Good. Even though still the network server sees the encrypted data, so it will be able to alter it, but already that is a more far-fetched scenario.
I mean, this is what you...
Yeah, so here's the same, this is the picture. So the device is on the left, and it has a custom program running that encrypts the data, and then the LoRaWAN layer will also encrypt the data with the network key.
So it's the second layer, basically.
Yeah, then it travels through the whole to the antenna, to the gateways, and then in the end to the network server.
Because, if I may, that's also a complaint because of LoRa long range. We hear some people being scared that if you are across basically our industrial site with your own gateway, you could pick up the messages of the nodes yourself.
Yeah.
But if you look like this, the gateway itself is completely outside the encryption layer, right?
Yeah, the gateway is it just passes on all the messages as is.
So I could listen up, but just get
if you listen for packages, if you park your car next to this site, and you start listening, you will receive encrypted or double encrypted blobs. And theoretically, you could say I am going to join that network, and then I will start injecting packages. Well, that is not possible because the network server the application server that we use does not process any messages other than the ones we know. So we whitelist our own devices.
The extra layer of security.
You could also sit next to the site and replicate packages or resend them. That is also taken measures for by taking frame counters. So we keep track of the counts, and then
something is off.
And the counter itself is inside the double-layered encryption. So and then another thing is that if you use keys for too long, you can say, okay, now I want to break that session, and the device will reconnect, and because it will not be able to send anymore, and the device will know this, and then it will say, okay, I am going to rejoin, so there will be a new set of keys.
That's where the join server comes in again. Yeah.
Exactly. Yeah.
Okay. And then you have the same discussion, I think, right?
Yeah, exactly. Yeah. So we touched on it before. So if you go private, then already the network server is a trusted element, and your application server is a trusted element. So that makes making this
the chain of control
secure makes it much easier and more reliable. If you go to a public network, you can still rely on the one layer encryption and frame counters. Yeah, so it's a bit of a risk trade-off.
This is where it ends for you normally, right?
Yeah, so this is where it gets really interesting for me.
Connectors, yeah.
Then you have an application, and it decodes the final payload, and you have the raw sensor message, so the temperature is, or the...
You finally have it all figured out, you know what the message is.
The valve is open or closed, and then you have the data, and then that is where actually the application begins for the customer. So how do we get, so the first question is, how do we get the data at the customer? There is a ton of protocols that you can use. Industrial sites often...
because there's also something that's, if you normally look at public LoRaWAN networks, they often MQTT or like an open API type of thing.
Yeah, you either have to poll through an API or you have MQTT.
But that's like all web technology, but the industrial sites that we operate, the DCS systems where you might want this information, they don't have this kind of API.
No, they want, for example, OPC UA, and that is something that we are able to transform our messages into OPC UA objects, and once the message comes in, we can update the tags in there, and customer will be able to retrieve the data from that OPC UA server.
And through OPC UA directly into DCS.
And it will provide direct DCS integration. Yeah.
But that piece of software needs to be run locally, anyways.
Usually it is run locally because of already the network restrictions and security requirements on that level.
So
so high
that's why it also makes sense to end the whole network server on the same locally.
Yes, if you have a machine running only that software, then it makes sense to just add those components because they are relatively simple and lightweight, and compared to because LoRa network packages are really small, and so if you have a virtual machine or something running, then you're able to run an application server, then the rest is also a piece of cake.
I think piece of cake is a nice place to end. After we spent 45 minutes explaining you that it's actually just a piece of cake.
Yeah. In the end, when it works.
Let's see if everybody agrees and if we have any questions from this point forward.